Okay, in this video we're going to discuss on how we can measure time constants using an oscilloscope. And you know, in practice we're not necessarily going to be measuring a lot of time constants in the workplace, but time constants again are so important. They're used all the time as far as in other IC chips and other to set like frequencies and other things of that nature. So this concept of a time constant is very important. And recall here for an RC circuit, the time constant is R times C, and that for an RL circuit, the time constant is L divided by R. Now I am going to do two circuits here to demonstrate how to measure time constants. The first one we're going to do is, they're going to be very similar to the ones you do in the lab. It's going to be just an RC circuit. And I'm going to measure the output voltage here. And then this is R, and this is C, and well, of course they are. Should give you some values. This is at 1 k ohm. This is 1 microfarad. And then this is going to be 4 volt peak to peak square wave, which you'll have to use your audio generator to create. And I'll show you how to do that in a little bit here. Now, before we do this, you should first measure component values. And when I measured my component values, I got that my resistor was equal to 0.979 kilo ohms, and then my capacitor is equal to 1.053 microfarads. And I'll show you measuring the capacitance yet, because you probably have never done that before. And I'll also show you how we have to be a little bit careful with the capacitor that we're using. Okay, so we're going to measure the component values. And we do this because even though on the diagram it says 1 kilo ohm and 1 microfarad, we want to get as accurate as possible as what a time constant would be here. So tau is equal to, here, R times C. So we just do 0.979 kilo ohms times 1.053 microfarads. And when you do that, I wind up with that this is approximately 1.03 milliseconds. All right, now, so we have that there. Now the next thing here we want to look at is how many time constants do I need to display, because I'm going to have to, notice here I didn't set the frequency. We're going to have to determine what the frequency is, at least as an initial starting point to set this. And remember, it takes about 5 time constants to charge or discharge. So we're actually going to do 10 time constants. And the reason we're doing 10 time constants is it would take 5 time constants, for instance, to go from 0 to 2 volts, but it would also take another 5 time constants to go from 0 to negative 2 volts. And since our thing is going between positive 2 volts to negative 2 volts, that's a total of 10 time constants. So we're going to do 10 time constants. So 1.03 times 10 gets me, of course, I don't know why I had to use my calculator for that. 10 time constants gets me 10.3 milliseconds. Now, to get frequency frequency is just 1 over my period. So I'm saying I need 10 time constants. So I'm going to do 1 over 10.3 milliseconds. And we get approximately 97 hertz. Now, of course, we can't set this to exactly 97 hertz, and even if we could, it's not necessary. So we're just going to round this to our nearest setting on our audio generator, which is 100 hertz. And that's where we're going to start. That's not necessarily what we're going to use, but that's where we're going to start. Okay, switched over to the camera here, and I've already kind of built the circuit, but I'm going to show you one thing here that the capacitor I'm using here, let's see if it will even focus in on it, might not here, is an electrolytic, yeah, it's not focusing in on it. It's an electrolytic capacitor, and I know it's 1 microfarad because if you kind of scroll around on it here, on this side, it actually tells me that it's 1 microfarad. But then also you want to notice here there's this negative side of it. It matters what direction we put this in. I can't just randomly put this in any direction. I have to make sure the negative side goes to the negative side of the circuit. And so the negative side, if I go back to my circuit for a second, the negative side, of course, is just going into my ground right here. It's going into my ground. And then the positive side is connecting to the 1 kilo ohm resistor. Now, before I connect that up, I want to show you how you can measure capacitance on your ohm meter here. So we've got our multimeter here. It's set up in standard mode. And if I look here, this is the setting we do for measuring resistance all the time. And, that's how I measured the resistor value, just typically. But then if I hit a mode here, there's different modes. This is like a diode test mode. This mode is actually very useful for determining if you have shorts or if things are connected. Basically, if there's a short or if it's connected by a wire here, I'm going to show you just by touching the 2 leads together here. You get that annoying little buzzer, but that can actually be very helpful when debugging circuits. Now, if I hit again another mode, we can see an NF comes up for nanofarads. So now I'm in the mode of measuring capacitance. Now, I'm still going to make sure that I take the, let me adjust here. Oops, I want that to be full screen. Okay, so I'm going to take my little probes here. I'm going to put the positive on the positive terminal of the capacitor, and I'm going to put the negative on the negative terminal. The other thing is, if you look here on these leads, the positive lead is always longer. So I'm going to touch them together like this. So you can see I'm just touching them together. And this time I'm reading a 1.071, but when I measured it earlier, or 1.074 microfarads, but when I measured it earlier, it was at 1.053. And so you want to use those actual values to compute your time constant, because we want to be able to look at it and see if we can measure that time constant and get the same thing. All right, so let me move this to the side, and let's look at our circuit here. I'm not going to go through on how to build this circuit. This is a very simple circuit, but I am going to emphasize one more time here that this positive terminal and this negative terminal, well, I'm going to connect the positive side into my resistor, and I'm connecting the negative side into ground. So let's look at what I've got going on in this circuit here. Let me raise the circuit up here so you can focus on it. So I've got a 1 kilo ohm resistor right here, and I've connected it to this orange wire, and this orange wire is going into the positive rail. Then if I follow this orange wire, I'll just bring it in forward, that is connected to the positive terminal of my audio generator. Now I'll say function generator but function generator and audio generator, same thing. Now, if I look here, then the other side of the resistor, let me take this cable out for a second. The other side of the resistor is connected to the capacitor. The capacitor is then going to the other side, which is connected to this wire, and that wire goes into ground. Because if I look at this one right here, this black cable, I'm connecting to the negative terminal of the audio generator, so that's ground. Okay, so let me put a couple things back in here on this circuit so that we can get this to start running and doing some measurements. Okay, so I've just put these back in. And what I've done is I've put the oscilloscope probe in parallel with that capacitor. So I can measure the voltage across that capacitor. Because that's what we're wanting to do, is see what the voltage is that's going up and going down. So now I'm going to turn my audio generator. One, remember it's got two different forms here, sine wave or square wave. So I'm going to put it in square wave form. And then I'm just going to turn the dial to 100. And I've already got the amplitude set correctly, but you can just measure the signal to make sure that the amplitude's set correctly. The amplitude honestly isn't that big a deal. We just want to make sure that we have something to charge up to and something to charge down to. If you set the amplitude at the maximum, it's not going to make a difference. Now you can see here we don't necessarily have anything. Let me actually turn my cursors off here for a second. We don't have anything displayed on the screen. So I'm going to see if I can just do an auto here. And do I not have something connected correctly? I always run into this here, just like you probably do. Let's do a quick little search on here. See if we can see anything obvious. I know, I did it again. I had it set in the wrong frequency range. I had the times 100 thing on, and I need to be in times 1. Because I want 100 hertz, not 100 times 100 hertz. So let's do another. There we go. Now, what we can see here is that this is showing the capacitor. Now this is ground, remember, right here is ground. We can see the capacitor charging up, and then it's discharging. Now, we can't see the full behavior of the charging and discharging, and this is where you have to play with, we're going to play with the frequency a little bit. Now I'm going to turn it up to 120, and then I'm also going to do it up to 150, and if we keep doing this, we can actually see that the amplitudes are getting smaller here, because basically we're turning up the frequency, which means we're not giving it enough time to charge up and discharge. So I don't want to turn up the frequency, I want to actually turn it down. And as I turn it down, we're going to have to do some adjustments here. You can see we can start seeing it flatten out more, because now it's hitting my full charge. I'm going to actually adjust my vertical scale a little bit there. So you can see it's starting to flat out. I'm going to even go down one more here, and you can really see it flattening out now. So you can kind of see it charging up and then discharging. Now, for measurement purposes, we don't want it too flat. Like this, actually right here would be a good curve for showing up charging and discharging. And the reason we don't want it too flat is we want to make sure to get as many data points in here as possible, and we don't want to waste data points on it being flat, you know, because that's not useful to us, because okay, it's flat. But I wanted to show here, and I'm just going to go back again, that eventually this capacitor will charge up, and you know, I'm now down at 20 hertz, and you can see when you're doing at 20 hertz, this capacitor is fully charged for this time interval. It's fully charged at this time interval. And then because we're switching the square wave, you know, that's why we're getting this particular shape. But again, we want it so that we can actually measure some time constants. So I have this set at 64 hertz right now, because I get a nice, I mean, it's not, I don't have the full flatness, but I've got it close to there. So that's what I want to do there. Now I'm also going to adjust the time scale so that I don't see a bunch of these. I really only need to see one. Okay, so now this is where, if you've watched the video, we have to do a little bit of computation here. So what I'm going to do is going to turn my cursors on here. So cursor mode is going to be, and you want it on track, because then it's going to track on the actual graph. So I'm going to turn those on here. And then what you want is cursor A and cursor B to both be on the channel that you're using. Now I'm using channel 2 just because I like blue. So that's the reason I'm using channel 2. You could be using channel 1 and that's fine. But here, you know, I want both cursors A and B to be on the same channel. And then these two buttons here determine which cursor we're actually moving. So what I'm going to do here is I'm going to move some of these cursors. Oops, wrong knob. I'm going to move some of these cursors here. And so we can kind of see what we're going to do here. So again, if we follow the video, what the video told us here, so we're going to set one of these cursors. And I'm going to set cursor B here. I'm going to set this to be just some voltage right here. So cursor B's X value is 2.5 milliseconds, or 2.560 millisecond, and it's fluctuating between 1.48 and 1.52 volts. So since it's fluctuating between those two, I'm going to do the average of that. And that would be 1.5. I can't see my screen, so I'll just do that. 1.5. And now we're trying to measure one time constant. And in one time constant, we will still maintain 66, roughly 66% of the value. And if you looked at the video, it's precisely, not 66, 63.2%. So we're going to take 1.5 and multiply it by 0.632, because that's 63.2%, and we get 0.948. And so we're going to look for and try and set the other cursor now. So I'm going to move cursor A, and I'm going to try and set that at 0.948 volts. Now, be careful that you're checking to make sure if you're positive or negative, but I'm going to say 0.948 volts, or 948 millivolts, because it's giving me millivolts here. Now, I'm not going to be able to get this exactly because of the data points on this. So I've got 9.2, 0.92, and 0.96. And so we can see here that neither one of these is particularly great as far as this goes. And I'm going to just leave it at the at the 0.961 there. And we can see here we get a delta x. Now delta x is actually my time constant. And so we can see here, well, wait a minute, I computed my time constant to be, if we go back here, I computed my time constant to be 1.03 milliseconds, and I'm getting a time constant here of 1.44 milliseconds. And there's a couple reasons for this, and you should think about this and discuss this in your lab report. One, of course, we can have tolerance errors, but that's always the case. You can have tolerance errors. But tolerance errors are things that, well, we always accept that that's going to be the issue. But a main issue here is notice how coarse, and when I say coarse, I'm jumping 0.04 millivolts every time I move my cursor. So I can't fine tune it to the voltages that I need. And the other thing here is that there are actually stray capacitances in this breadboard that can affect time constant measurements like this. Um, and so there's a lot of other things that can affect our measurements here. So if we want to try, what you can do is it's like, okay, well, I want to increase my scale even more. And then if I increase my scale even more, which one am I moving here? Oh, yeah. I'm going to, so I increase my time scale even more here so that maybe I can even capture a little bit better here. And so what I'm going to do is I'm going to do essentially the same thing. Go to channel B. And okay, we put it at like 1.4. And then I'm going to go back to channel A. But you can see we're still going in steps of 40 millivolts. And that has a function to do with just how many samples that this thing is taking. And I'm just trying to see here. Yeah, this doesn't have the ability here. Some oscilloscopes have the ability to change like how many measurements, and there might be a way to do it in here. But the point here that I'm trying to make is how you can measure the time constant. And we're doing it the exact same way as the video.